Alright, so we are looking at section 6.4, which is looking at arc lengths of curves and surface areas. And they kind of like tie into each other pretty well, so that's why they're in the same section. But first we need to think about the distance formula. So do you remember what the distance formula is? Because the question is, what is the distance formula? It's remarkably similar to the Pythagorean theorem, so you have like a squared plus b squared equals c squared, right? If we're looking at, instead of c, let's call it distance, and instead of a and b, we're going to do these like a change in x and a change in y, so then we get, so like change in x squared plus change in y squared is the distance. So if we're square rooting all of that, there you go, distance formula. So from our distance formula where we have root, and then we'll change those delta x and delta y's to x2 minus x1 squared plus y2 minus y1 squared. There you go, that's the classic distance formula. Why is that helpful? Well, if we're generally looking at like a graph, like a curve, and we want to accumulate all of the distances between very small segments of this, then there is a way to do that using integrals, right? Because if we're looking at a small change in x and a small change in y, and then we're looking at the distance that's traversing, we can utilize our understanding of definite integral as an accumulation, and we can leverage that to help us to figure out how long a curve is, which is really cool. I mean, like, if you're, cause we can think about things as in terms of approximations and trying to measure things with straight little secant lines, and that's great, and that can get us pretty close, but to actually measure a curve that isn't necessarily a circle or an ellipse, like how long it is really cool. So, that's what we're doing next. So if we look back at this distance formula where we had the delta x and delta y's, what can we do to this maybe to break a delta x out? So suppose we wanted to factor out a delta x from inside the radical. Well, we would have a 1 there because delta x squared, when you're taking it out of a radical, that's just 1. And then we have plus delta y over delta x squared, right? And that equals our distance. And that, that's just factoring out that delta x, right? Since we know that the mean value theorem guarantees the existence of some, like, c in our interval from like x sub I minus 1 to x sub I, like some interval that we're looking at, we are guaranteed that f prime of c is going to equal f of xi, f of xy minus f of xi minus 1 over xi minus xi minus 1. We're looking at the slope of our secant line has to equal the slope of our tangent line somewhere on our interval, because we're assuming that we have a continuous curve. Right, so from there we can rewrite the what's highlighted in yellow, this delta y over delta x, which is exactly the same as this, right? So what we get is we get delta x root 1 plus f prime of some c value squared, and this equals our distance. Now, if we're trying to add up all of these distances, we want our delta x to get infinitely small, and then we're going to add up, so we're going to sum all of these delta x times 1 plus f prime of c, which is all of our distances, and we're going to add up all of the things that we need. So this is actually going to give us as we're adding up, we're going to get an infinite number of things that we're adding together because our interval size is getting infinitely small. So, if we think about that, I mean, that looks remarkably similar to our integrals stuff, right? Because our definite integrals are an infinite sum where we're adding up an infinite number of little rectangles. So, what we can have is actually, let's scroll down. We have the arc length is our definite integral from a to b, because that's our smooth curves interval, of the square root of 1 plus f prime of x, quantity squared, and that's with respect to x. So the delta x is the dx, the 1 plus f prime of c, that's right there, and then we're square rooting all of that, and we're looking at an interval. There you go. And we can also do this with respect to y, because, I mean, if you just switch your x and your y, then you're going to get out the same distance, right? Because we could have factored out, instead of having in our distance formula, instead of factoring out a delta x, we could factor out a delta y, so we get dx dy squared plus 1, commutative property of addition, and we would get out the exact same thing, just with our variables swapped. So we can find the arc length of a smooth curve using definite integrals. So let's try it. How do you find the arc length from x1, y1 to x2, y2 on the graph f of x equals mx plus b? Well, we can do this the fancy way, or we could do this the not fancy way. The not fancy way is if you have a point x1, y1, you have a point x2, y2, and you have a line connecting them, then just what's the distance there? Pythagorean theorem, and you can find it, but that's like, less fun. So let's use calculus. What was our formula? We had our integral from a to b of the square root of 1 plus f prime of x squared dx. And we're doing this with respect to x because our function is in terms of x. We can also do it in terms of y, but that's more effort than necessary, so it's not. So what's our interval? Well, a is x1 and b is x2. And f prime of x here is just our derivative of mx plus b, which is the slope of the tangent line, and since our function is a line, then our tangent line is always m. So we have our arc length, and we typically call it s. I actually don't know why, so that might be worth a math journal. But we have our integral from x1 to x2 of root 1 plus m squared dx. And what do we get? Well, this whole thing is just a number. So we can use our power rule, and we get root 1 plus m squared x from x1 to x2, fundamental theorem of calculus, right? And so we get 1 plus m squared, and then x2 minus x1, because this thing is just a constant. And there we go. Cool. How do we find the arc length of the graph? Y equals x cubed over 6 plus 1 over 2x on the interval from 1/2 to 2. Well, let's set it up. So we got s equals integral from 1/2 to 2 of root 1 plus, and then what is y prime here? Y prime is 3x squared over 6. Oh, that was poor space management. Okay, so y prime is 3x squared over 6 plus 1/2 x to the negative 2. We need negative there. So then pew pew, that's a 1 and a 2. So y prime is x squared minus 1 over x squared over 2 minus 1 over 2x squared. I guess we can combine these two fractions. We get, what, x to the 4th minus 1 over 2x squared. Okay. This is going to be a lot of algebra. Alright, so this is x to the 4th minus 1 over 2x squared, and we're squaring that, and we're taking our definite integral with respect to x. Alright, so what does that give us? Let's continue to algebra. We got 1/2 to 2, integral 1 plus x to the 4th minus 1 squared is x to the 8. Wow, this is getting really terrible, huh? Minus 2x to the 4th plus 1 over, and then we have a 4x to the 4th dx. Oof. You know what? I wonder if there's a way that your calculator can do definite integrals. I wonder if there's a way to evaluate. Indeed there is. So if you have a TI 83, 84, I'm actually not sure how the other ones work, but you hit math, and then you hit 9, then you should get something that you can evaluate a definite integral for. I would recommend putting in this part instead of trying to, like, you know, finagle your algebra properly. And you also need to put in, so you put in the function, you put in the lower bound and the upper bound, and you put in the variable that you are integrating with respect to. And there should be, and then you should get a number out. Let me see if I can find a calculator and show you. Okay, so what did we get? We got this thing. That was so much effort. Okay, so click on the math button, and then see this FNINT, so that you can get to that by arrowing down, or you can just hit 9. This one's fancy, so it gives you like the little, like this fun interface, but if you don't have this, then you can use commas in between the things that you're inputting. So lower bound is 0.5, arrow over to the upper bound is 2. We're doing this square roots of 1 plus parentheses x to the 4 minus 1 close parentheses squared over, I did this poorly. Okay, x to the 4 minus 1 parentheses squared divided by 2x squared parentheses. Okay. I don't think I want the squared there. Let me just put the squared here too. And yeah, that works. Okay. Okay, cool. So we got an arc length, and it seems marginally reasonable. Right? How would we find the arc length of this thing on this interval? Do we want to do this in terms of x or in terms of y? Well, looking at it, it might be more straightforward to do this in terms of y, because if we have, like, we have all of this, right? That's kind of like containing our y, so it would be much easier to just use a square root. So we have square root of y minus 1 cubed equals x. And so now we have a function in terms of y. And we can still use our arc length formula. So we have our x value inputs, those are what we're given. We can figure out what our outputs are going to be, so our bounds in terms of y. Just plugging those in. So we have y minus 1 cubed equals 0. And when does that happen? When y equals 1, and we can see that right there. So we got a lower bound of 1, and then our y minus 1 cubed equals 8. When does that happen? When y minus 1 is 2, so when y equals 3, no, 8 squared. Oops. So then 8 squared is 4, so then we get this is 4, and this is 5. Okay, so we got our upper bound is 5. And then we're going with 1 plus our derivative with respect to y. Our derivative of g of y. And let's do that over here. So g of y is root 1, y minus 1 cubed. So g prime of y is going to be 3/2 times y minus 1 to the 1/2 power. And then with the chain rule, we're going to take the derivative of y minus 1, but that's just 1. So here we go. We got 3/2 y minus 1 to the 1/2 power. And all of this we are squaring because Pythagorean theorem, right? And then this is with respect to y. And again, that looks kind of gross. Not terrible, though. I might clean it up a little bit before I try to chuck it into the calculator. So we get what? 1 plus 3/2 squared is 9/4, and then y minus 1 to the 1/2 power squared is going to be y minus 1 dy. So let's try to put that in the calculator, see if we get any faster at this. Probably not. So math, and then we want 9. Our bounds are from 1 to 5. And we can put this in terms of y and all that, and I guess we can do that. So we get square root. So square root of 1 plus 9/4 times, and then alpha to get y. Okay. Minus 1, and then close that parentheses. Alright. And then we arrow over and do this in terms of y. What do we get? Cool. We got like 9.073. Does that vaguely make sense? Well, if we're looking at a distance from here to there, it makes sense that it's not like a gigantic number, but it also makes sense that it's like, more than like 5, right? Because if we're looking, it's a pretty good estimate. Cool. Alright, so let's check the arc length for this. This is in terms of x, and we'll leave it like that. Y prime is 1 over cosine of x times derivative of cosine is negative sine of x. So what's that? Negative sine over cosine. And what do we get? Well, s equals integral from 0 to pi over 4 of square root of 1 plus negative sine x over cosine x. That is... Isn't that tangent? Negative tangent? So we got negative tangent squared dx and we can find that. Isn't that secant? I feel like that is 1 plus tangent squared, because cosine squared x plus sine squared x equals 1. So if you divide everything by cosine squared, then this is 1 plus tangent squared x equals secant squared x. So that's nice because then everything in here is just secant squared. So we get integral from 0 to pi over 4 of secant x dx, and that is just lovely, right? Because we can just put that in. Math 9, integral from 0 to pi over 4 of secant, which is 1 over cosine of x with respect to x. .881, and that seems about right. Cool. All right. So, we talked a lot about arc length. There's surfaces of revolution as well. So if you take an arc length and you rotate it about an axis of rotation, then you're getting a surface. So, that's the general idea. We can have our little, like this is a nice little picture where we have, this is an arc length. It's a poor color choice. We have this little arc length right there, and that's getting revolved around our axis of rotation. So once again, it's helpful to draw a picture. If you're doing a surface, I do recommend that you draw the representative rectangle so that we can see what's being rotated. I wonder if, you know, our cylinder stuff is going to come back. I think so. So if we're looking at a surface of revolution, the things that we have are an arc length, which is like a height of a cylinder. And then we have an axis of rotation that gives us a radius. And well, like based on the shell method, right? We were looking at just cylinders as like surfaces that were accumulating. So if we're just looking at the surface area of our cylinders, then there we go. We get it. We get a surface of revolution, and as long as we're incrementing in the right direction, then we're good to go. So our surface of the surface area of a revolved thing is when we have 2 pi times the integral of our radius of the revolution times the arc length, or times this like rearranged Pythagorean theorem, which gives us the arc length. So we can do this also in terms of both x and in terms of y. And so let's try some problems. So the area of the surface found by revolving this graph x cubed on the interval from 0 to 1 about the x-axis. So we're going to have our representative rectangle going this way. So we get an arc length there, and we have a radius, which is not too bad. Or there we go. That's a better picture. So our radius is based on the distance from our axis of rotation to the curve that we're looking at. So that's what our radius is, and that's just x cubed. If we had a different axis of rotation that was off of our like coordinate axes, then we would shift this. And then we just have the other part of our arc length stuff. So we have f prime of x squared, so f of x equals x cubed, so f prime of x is 3x squared, and you might be able to do that in your head, and that's awesome, but I recommend writing things down. It just helps organize everything. The longer I stare at a math problem without writing things down, the more confused I get. So it really helps me to write stuff down. So this is going in here. So then we get 2 pi, it's right there. So we get 2 pi times our interval, which is going from 0 to 1, of our radius, which is x squared, or x cubed, times our Pythagorean theorem with the root 1 plus 3x squared, quantity squared, plus times with respect to x. Okay, so, and then you can plug this into your calculator the exact same way. You should get a number. And last but not least, find the volume and the surface area of a solid form by rotating about the line y equals 0. So the line y equals 0. The region bounded by the line x equals 1. This is x equals 1. X equals 100. Y equals 1 over x. So we get this. And the x-axis. So that's our region that we're rotating, and it might, like, if you can think about it in terms of our little representative, that's a poor choice. In our representative rectangle, that's what's getting rotated around. So we get something like this. And what's the surface area of this? It almost looks like a vuvuzela. Remember those from like 10 years ago? But we can have a, so we have our bounds from 1 to 100. We're looking for our surface area, so we just need 2 pi out front, and we need a radius, and our radius, because our line that we're rotating about is y equals 0, that's just going to be our function 1 over x, and then that's times 1 plus, and what's our derivative of y? That's going to be negative 1 over x squared. So we got 1 over negative x squared dx, and then just plug that in, see what we get. This is very like imagine instead of 100 that our bound like n was going to infinity. Like thinking about the n behavior of what this shape would be. It's very interesting. Might be worth journaling about. We are going to look at it later, but that is something for next semester. But Gabriel's horn. Something worth looking into. Okay, that just about does it. Yeah. I don't have anything else. Sorry. Yeah. There we go.